Dear students, welcome back. In the previous lecture, which is lecture 31, we had seen the method of variation of parameter. In this lecture, we are going to introduce the method of power series solution. Okay, so this is a technique which you can employ in cases where you can't use the other types of elementary method. Okay, so it's kind of an additional method where all the methods that you've seen so far, if they don't work, then this may sometime help. Okay, so to start the method of power series solutions, so let's first look at the definition of analytic function. Now, why are we looking at the definition of analytic function? Is that if you take an ODE, let's take a first order ODE. Okay, let's take a linear first order ODE. So usually a linear first order ODE, as I said, will be something like a1x, a0 x, y, and then let's take homogeneous. So this is the form that you will have, which is what we have introduced in terms of PQR. So you can always normalize a ODE of this form, because if this is an ODE, then we have said if it's a first order ODE, then this coefficient should be a non-zero function. That is so this is not the constant function 0, right? Which means that you can divide. So if it's a non-zero function, you can divide and you can actually normalize. So any ODE of this form can be written in this form. Okay, so in general, I could start with an ODE which is the normalized form. Let's say Q, Y, this is the normalized form. Okay, so why are we introducing analyticity? So you see, when we say power series, you already know what is a power series. So any function, if you are given any function, and if it has the power series form, then you say it can be written in this form, right? K0 to infinity, right? Some coefficient, then x power k. Okay, and if it's power, so this is power series about the origin. If you want power series about any point x0, then you say this. Okay, this is the power series. So this is the notion of power series. So now we are going to take ODEs and we are going to seek power series solution, that is solutions which are of this form. Okay, and so writing a function in this power series form has a special name in the real variable setup, in fact even otherwise, so which is called the analyticity, like analytic function. Okay, so what is an analytic function? So a function f is said to be analytic at any point x0 if its Taylor series about x0, which is precisely this, right, exists, right? And when we say exists, means that this series is there, which means the function f is differentiable. It can be evaluated at, so it's differentiable, so it's infinitely differentiable, and it can be evaluated at the point x0. And if you look at this series, the series converges, and it actually converges to f, and this happens for all x, that is f of x is equal to this. Okay, so whenever an f can be written like this, it's so then you say f is analytic at x0. Okay, so even here, if you know that a f has this form, this power series form, and if it's infinitely differentiable, you can actually show that these coefficients ak are the kth derivative of f evaluated at x0 over some constant. Okay, so this is the ak. Okay, this you can show, right, how, because if it's infinite differentiable, you differentiate then you will see that, I mean, if you plug in x equal to x naught, then many terms here will 0. Only the leading term here will stay, which where the k was equal to 0. Only that term will stay, right? And, so for instance, for f of x naught, it's always a naught. If you differentiate, so then you will have the leading term a1 here. So then you will have f prime of x naught is a1 and so on. So you can actually show that if a function has a power series form, then the coefficients has to be this, right? So alternately, so a function is analytic if you can express it as a power series. Okay, this is the Taylor's form. Okay, this is the Taylor series. So that's an analytic function. And why are we looking at analytic function? Because if you are going to look for power series solutions of an ODE, then it so happens that you can do that only if the coefficients are analytic. That is, you are looking for an analytic solution, and that automatically imposes that the coefficients also have to be analytic. That is the reason why we are looking at the definition of analyticity. Okay. So let's look at some examples. Like your exponential is an analytic. You know that is a series form for e power x, right? That is analytic. This is one example of analytic function, right? All algebraic polynomials are analytic. Okay, and sine, cosine, they are all analytic because you know there is a power series expansion for both sine and cosine, and they are all analytic everywhere. So what do you mean by analytic everywhere? It's analytic at every point of the domain. Okay. Now the reciprocal of all these functions are also analytic except on its roots. So these functions may vanish at some points, right? So except those points where they vanish, in every other point the reciprocal of these functions are also analytic. Okay, these are all examples of analytic function. I am sure you have seen this in the previous course. You must have seen analytic functions. So this is just recalling what are analytic functions. So now let's give the definition of an ordinary point. So basically we are going to look at the power series method for a second order ODE or even higher. Can I do it for first order? Yes, you can do it for first. So when I say normalized form, I basically mean that the leading coefficient has been divided here. Okay. So there is no coefficient. I mean, so you basically make the higher order derivatives coefficient 1. Okay, by dividing. That's what is called normalized form. So if you take the normalized form of a first order ODE, then you know it's something like this. Right, homogeneous. So it's a homogeneous ODE here, right? So if you take this, we have already solved this in the previous lecture. This is a linear first order ODE, and we have already shown how to solve this. We have this method of integrating factors, and you can actually precisely solve this without using the method of power series, right? So we can solve it, but you can also solve this using the method of power series, and you will get the same expression for general solutions and so on. So we will not explain the method in the first order. Whatever we are going to explain in the second order is also applicable for first order and so on. Okay, so what is an ordinary point? A point x naught in the domain is said to be ordinary point of the given differential equation, which is, let's say, second order linear homogeneous. So this is a second order linear homogeneous ODE, which is in the normalized form. So you say any point x naught is an ordinary point of this differential equation if the coefficients that you have in the differential equations p and q, they both are analytic at x naught. So if the coefficients of the linear homogeneous ODE is analytic at a point x naught, then the x naught is said to be an ordinary point. What does this mean? That p and q are analytic at x naught, that there is a power series expansion of both p and q about x naught. Okay, that's what this means. Now if one of them, I mean either p or q or both p and q are not analytic at x naught, then you say x naught is a singular point of the differential equation. Okay, so if P and Q are analytic at x naught, you call it you call the x naught as an ordinary point, and if at x naught P and Q are not analytic, either one of them or both, then x naught is a singular point of the ODE. So there is a notion of ordinary point and singular point corresponding to a differential equation, which depends on the analyticity of the coefficients of the ODE at that point. Okay, so let's look at some examples. So for instance, if you take this second order ODE, here if you look at what are P and Q, P of x is x and Q of x is x square plus 2, right? Are they analytic? They are analytic, right? They're already in the form, right? Analytic form. So they are analytic at which point? At actually all the points in the domain R, right? For every point in R, P and Q are both analytic, which means all the points are ordinary point of this differential equation. Okay, right? Because here this is, if you write it, if you want to see it in the, if you want to see in the any power series form, right? So you can always see it. For instance, let's take at x equal to 0, if you want to write it as a power series, then this is already in the power series form, right? Every other coefficient is 0 except x power 1. Right? All AKs are 0 except when, except for k equal to 1. Similarly here, all AKs are 0 except for k equal to 2 and k equal to 0. Right? So this is so all the points here are ordinary points, and this you can do for every point, not necessarily 0. Okay. Okay. Now, what about this ODE? Okay. What is a P here? So here you see there is a leading coefficient. So this is not in the normalized form. So to check for ordinary point or singular point, you need to convert this into a normal form. So normal form is y double prime plus x over x minus 1 y prime plus y x minus 1 equal to 0. So your P is x over x minus 1, and what is your Q? Your Q is 1 over x into x minus 1. So what are the points where, every other point is ordinary point except when x equal to 0 and x equal to 1, because for x equal to 1, P has a singularity, right? X equal to 1, so it blows up, whereas for Q, it has singularity at both x equal to 0 and x equal to 1. So therefore x equal to 0 and x equal to 1 are singular points of the given ODE, because the coefficients blow up at these points. Okay, so this is how you check ordinary point and singular point. And why did we introduce this notion of ordinary point and singular point? That you will see very soon, that to look for a power series solution, this is very important. As we said, power series solution depends on the analyticity of P and Q, and ordinary point and singular point is a definition corresponding to the analyticity of the coefficients. Okay, so this is an explanation of this. So in this case, P, as I said, is x over x minus 1 and Q is 1 over x minus 1, and both are not analytic at x equal to 1 and x equal to 0 and 1. Right? P is not analytic at x equal to 1 and Q is not analytic at 0 and 1. So all points except 0 and 1 are ordinary points. Okay, so this is an example. So these are an example for ordinary points and singular points. So now let's move to the main result of this lecture, which is which tells you that if you have a second order linear homogeneous ODE second order linear homogeneous ODE of this form, which is in the normalized form, and if x0 is an ordinary point of that ODE, then this, and we have already seen in the earlier lecture that for a second order ODE which is homogeneous, you are going to have a two-dimensional solution space, right? That's what we have seen. So if we find two linearly independent solution, we have found all solution. And this theorem tells you that if x0 is an ordinary point of this second order linear ODE, then this ODE admits two linearly independent power series solution of the form, which is the power series form, such that the power series converge in some interval containing the point x0 where it is. Okay, and this power series is about x0. You see that? So it's a power series written about x0, centered at x0, right? So this theorem tells you the existence of two linearly independent power series solution, and they converge in some neighborhood of x0 or in some interval. When I say neighborhood, I should not use that word here. I mean, since you don't understand that, what I mean here is that x0 is some real number, right? And what we know is that x0 is an ordinary point in the domain. So this x0 is coming from the domain of this function y, right? Whatever is the domain of D, which is a subset. So this D is a subset of R, right? So this x0 is in some D, right? So in some neighborhood of x0, the power series converge, which means the solution exists in that neighborhood. If you recall from your Picard's existence theorem and so on, which we have done in the earlier lectures, you know that the existence is usually shown in a neighborhood, right? There is an H, right? There is an H such that the solution exists in x0 minus h comma x0 plus h. Okay, so that's the statement of this theorem. We will verify these things via some examples. Okay, we will not prove this theorem directly, but we will verify it via examples. So let's take an example of a second order ODE. So here you see what is your coefficient p, which is x, and what is your q, which is x square plus 2. Okay, second order ODE. And from here we know that all the points are ordinary points because the given functions are analytic by itself. We have already seen that in the example that the same example that we did before, right? So all the points are kind of ordinary points here. Okay, so let's find a power series solution about the point x0 equal to 0, right? So we are looking for a solution y which is of the power series form centered at 0. So we are looking for a y which is of this form. Okay, so can we find a solution to this ODE of this form? So how do you verify that? How do you know that? So suppose you want to find a y of this form. So finding y is same as finding all the ck, right? If you know all the constant here, that means you know y. So we need to find all ck. Okay, but in this case it's an ordinary differential equation. It's not, we are not given any initial condition, so we need to find the general solution, right? Basically we need to find two linearly independent solutions, power series solutions. So what you do, you just plug this information here in this ODE. Wherever you have y, you use this power series. Wherever you have y prime, you use a derivative of this power series. And here when we write this, we assume that we can differentiate term by term here, right? And similarly second derivative. So if you do that, so let's compute y prime. So if this is y prime is this, and y double prime is this, right? You just differentiated this y here once and twice. Now use this information in the ODE, given ODE. So if you use this form in the given ODE, this is your y double prime, okay, and this is your y prime Okay, this is your y double prime. In the y prime you had an x, right? The y prime you had an x, but y prime is this. So if you multiply an x here, you get an x plus 1 here. So you right, you get an x power 1 here, which will cancel with this, so you get x power k, and that's what we have here, x power k. And this is precisely x square plus 2y. So the x power k has become, so this 2 becomes k plus 2 and this becomes k. So this is just the ODE that we started with, and that's equal to 0. Okay, so now here if we need to arrange these things, we have to write everything of similar powers. So we have x power k here, x power k here, so we also try to rewrite these in terms of x power k. Okay, so what we have done is that we have just renamed. So here what I have done is that we have just called k minus 2 as a new k. So k minus 2 becomes new k, so all this will change accordingly like this. So this becomes k to 0, x power k. This remains as it is because it's x power k, x power k. Here again we do the same thing. We do k plus 2 is the new k. Or k minus 2 is the new k. Okay, so am I right? Yeah. So basically what I'm saying is that if you put k equal to 0, it starts with x square here, right? So we start with k equal to 2 and you make this x power k. That's what we have done here. And similarly here it remains same. Okay, so this this equation becomes this equation after rewriting everything of x power k. Now you can combine the coefficients of x power k. If you do that and then you equate it to 0 and then you equate the like powers both sides. So if you do that, you get 0 equal to, this is the coefficient corresponding to x power 0, this is the coefficient corresponding to x power 1, and then you have this coefficients corresponding to k bigger than 2. Okay, if you equate, you see it's all 0 here. So all the coefficients here are 0. So by equating like powers of x, you get from the first equation here, this equation tells you that C2 is minus C0, right? And as we said, we need to find these constants, right? So C2 is minus C0. So the C2 can be replaced with minus C0. Now if you replace here, this is 0. From there we get C3 is minus C1 over 2, right? And here you have this coefficient, right? And that gives you this recursive relation. So for k bigger than or equal to 2, right? So for k equal to 2, what you get is C4. Similarly, k equal to 3, what you get is C5, and so on. So on, you get all the constants, right? You can find. But here this depends on k and k minus 2. So when you want to put k equal to 2, so it becomes C2 and C0. But C2 is again in terms of C0. So this entire thing depends on C0. So C4 depends on C0, right? Similarly, C5, if you put k equal to 3, this is C3, this is C1, right? But C3 again depends on C1. So C5 depends on C1. So in this, if you actually keep doing this, all constants with even indices, right, even subscript will depend on C0, and all constants with odd will depend on C1. So finally everything will reduce down to constants, some functions multiplied by C0 and some functions multiplied by C1, right? Because all constants can be reduced to either C0 or C1. right? So therefore, as we said, C4, if you use that equation, C4 is depending on C0, C5 is depending on C1, so on. You can go on, and you can actually kind of show that if you use this information in the power series that we started with for Y, right? We wanted to find all the constants Ck, right? We had the series like this. We have found all Ck, and the first term is C0 and then C1, then everything else depends on C0 or C1. So you can separate them like that, those depending on C0 and those depending on C1. And here you see this is a series, this is a power series, and they are linearly independent because they are not constant multiple of each other, right? You cannot multiply a constant here and obtain this series. You cannot multiply a constant to this series and obtain this series. So these are linearly independent series, okay? And what you have Y as a linear combination of two linearly independent series, which means you have, so this is the general solution. This is the linear combination of two linearly independent power series solution. Okay, so thus we have verified the theorem. So here we were able to do this at the point x equal to 0, because x equal to 0 was an ordinary point. You could do that for any point as well. The only thing is, if you are going to do it for any point, then you need to start with the power series x minus x naught power k, and then use the same thing, whatever we did. Okay. Okay. Let's look at an initial value problem as an example. So let's look at this ODE. Now so we are going to look for a power series solution of this. This is not in the normalized form. You see there is a x square minus 1 as the coefficient. Okay. So you divide it. So you get P is 3x by x square minus 1, and Q, which is x by x square minus 1, and in both cases plus or minus 1 is a singular point. Every other point is an ordinary point, right? Now that's where you need to observe. This ODE we need to solve with this initial condition, where the initial condition is 0, right? So since we want to solve only about the point 0, we only need to check whether the coefficients are analytic at 0. If they were either plus 1 or minus 1, then we are in trouble. Then there are singular points. Whereas the point where the coefficients are singular is not going to affect the solution, because the initial value where you need to, the initial prescribed value is 0, so you only need to get a solution around 0. Okay, so in that case, this singularity, so the singular points doesn't really affect the solution. So because you are going to write down the power series of Y around the point 0. Okay, so the initial values are prescribed at x equal to 0, which is an ordinary point. So you can actually go ahead and look for a power series about the origin. Okay, though there were singular points here, but that is not going to affect, because our initial value is not the singular point. Okay, now you, as we did before, use this information in this ODE after differentiating Y. So then if you use that, then you get, and if you change the powers to be same, then you get an equation of this form. Okay. Now here, if you club the coefficients together and equate like powers of x, you are going to get recursive relations for all the constants. So if you do that, so if you equate the like powers here, for instance, x power 0, that is a constant function. So here there is no x power 0 because it starts with k equal to 1. Here also there is no x power 0 because it starts with k equal to 1. Here there is Here also there is no x power 0 because it starts from k equal to 2. So the x power 0 term comes only from here. So when k is 0, it's 2 into 1, 2, c2. There is a minus, so minus c2. Similarly, if you equate all coefficients, you are going to get these relations, right? So this is the power 1 coefficient. This is the coefficient for k bigger than or equal to 2. Now if you equate coefficients, you already see that c2 is 0, right? c2 is coming out to be 0 just by equating this to 0. Now if you equate this to 0, right, there is no c2 here, but you because there is no c2 here, so c2 you obtained to be 0. So there is a relation between c0 and c1 c3. So c0 3 c1 c3 is a relation that you get. Then you have a recursive relation for k bigger than 2. So the recursive relation that you get obtain is this. Okay. Okay. Now if I put k equal to k equal to 2, so then I can compute c4. So what is c4? So c4 is going to be given something in terms of c2 and c1, but c2 we have already seen is 0, right? So c2 is already 0, so this is 0, this term goes off. What you get is c1, so c2 0 plus c1 by, this is k equal to 2, so 4 plus 3 12, so it's c1 by 12. So c2 is 0, c3 is this, c4 is c1 by 12. c3 is from what we wrote before. From here, right, from here you get c3 is c0 by c1 by 2. Okay, here if you use this equation here, this is c3, which is 6c3 equal to c0 plus 3 c1, which is c3 equal to c0 by 6 plus c1 by 2, right? That's precisely what we have obtained here. c3 is c0 by 6 c1 by 2. c3 is c0 by 6 c1 by 2, and c4 we have already computed. Similarly, you can go on computing c5, c and so on. So c2 has become 0. c3 is depending on two constants, c4 is depending on c1, c5 is depending on c0 and c1. So you see, every odd, right, every odd index constant is depending on c0 and c1, whereas even will depend on c1. Okay, so finally you will get some class of functions which depends only on c0 and c1. So if you segregate c0 and c1, you are going to get y as a solution, as a linear combination of two linearly independent power series. And they are again linearly independent because you cannot obtain one from the other just by multiplying a constant or something. Okay. Okay. So now this was an initial value problem, so we need to use the initial conditions. So what is the first initial condition? The first initial condition is y0 equal to, so when x is 0, y is 4, and when x is 0, y prime is 6. So here, when x is 0, y is 4. So when x is 0, this entire thing is 0. So when x is 0, what you get is just c0. So c0 has to be 4. That is why we get c0 to be 4. Now if you differentiate this y, right, and then you substitute x equal to 0, that should be equal to 6. If you do that, so if you differentiate that, you get c0, this is the derivative. Okay, now you put x equal to 0. If you put x equal to 0, this is all 0. and this is all 0. What remains is just C1 using this. So C1 is 6. So C1 is 6. So you have got C0 to be 4, C1 to be 6, right? So that way you have the precise solution Y for the initial value problem. Okay. Okay. So we have seen examples both for the general solution case and even for the initial value problem setup. Okay. Now, so the previous example we have already seen that the coefficients were actually not analytic at the point x equal to plus or minus 1, but the initial point was x equal to 0, so we could solve that, no problem. So in the above example, instead of the initial point x equal to 0, okay, suppose say some other ordinary point, let's say x equal to 2 was given, right? This is true for any problem, because so far I have been only explaining when you write y expanded for x not equal to 0, right? Now you can always ask why I am not doing it at other points. You can do it at other points. So instead of x equal to 0, if you want to do at x x equal to 2 or some other ordinary point, then you have to start with the power series around that point. Okay, and then you can go ahead the way we have done. You will get a solution similarly as a linear combination of two linearly independent solutions. Alternately, you can reduce this problem to the previous problem, but so just by a change of variable. So if you introduce some s equal to x minus 2 as a new variable, then this becomes a power series in the s variable centered at s equal to 0, which is the x equal to 0 situation. So you do the same thing that you have done before, but before doing that you should rewrite the ODE in the s variable and proceed as follows. So you will still get the, so whatever we have explained so far about the point x equal to 0 is general enough, is what I am trying to say. If you have an ordinary point, you can actually translate, right? So you can actually go from, if you want to find the power series about any point x naught, right, you can do a change of variable and say x minus x naught and rewrite the ODE in that new variable. Then you just have to solve the problem for that s equal to 0 power series, right? So they are all same. Okay, so far when we have done all these things, we have not worried about whether the power series that we have written down is converging or not, and what is its radius of convergence and so on. All the techniques that you have learned in your previous course in calculus will work here, right? You can check for the convergence and so on and so forth. So here, for instance, what I am trying to say is that when we started with this assumption for the unknown solution y, the question is, how do we know that y will have such a form of a, right, kind of a, why will the y have a power series form? Need not be, we don't know that, which is why we are checking. But the fact that after making that assumption, we are able to come up with two linearly independent solution means that it has worked. So which means such a form had existed, right? So once we find the coefficients, we have never checked whether the series converge or not, right? That is that is part of the proof. One should actually do it, but at this level, let's not worry about it. Okay. Similarly, where does it converge? If it converges, what is the radius of convergence, right? What is the disk of what is the radius of convergence for this power series? That is also a question one needs to verify. These things we are not going to verify in this course, but these are the questions that you should worry about, is what I'm trying to highlight here. But there is a general, result which tells you that the solution will have the radius of convergence, which is minimum of R1 and R2, where R1 is the radius of convergence of P and R2 the radius of convergence of Q. So if you remember, we started with the assumption that P and Q, the coefficients of the ODE should be analytic, and then we start with a power series solution and we show that the solution exists, right? We show that there is actually a solution. Now the so the radius of convergence of the power series solution is at least as big as the smallest smallest radius between so the smallest radius of convergence of P and Q between them, whatever is the minimum. So if so, P has a radius of convergence R1, Q has the radius of convergence R2. So whatever is the minimum of R2, the power series solution is at least convergent for that radius of for that radius. Okay, that is something you all so for this level of the course, we will kind of assume that these things are something which we know, we don't have to worry about it. But these are things which one needs to check in general. Okay. Okay. So with this, I'll stop with the lectures. We will meet in the next lecture, continuing the method of power series for cases when the point is where the point is not ordinary, where the initial condition is not ordinary, where the initial condition is given on a singular point. Okay, so see you next class. Bye.